1999 National Electrical Code does require that the neutral conductor be counted when determining the ampacity of a feeder. This requirement exists because the neutral conductor carries the unbalanced current in a three-phase system. In a described scenario, the feeder is rated for 640 amps, while the generator output breaker is rated for 800 amps. This discrepancy indicates that the feeder is undersized. An undersized feeder presents a risk of overheating if the generator operates at full load, potentially leading to insulation damage, fire hazards, and equipment failure. The assertion that the authority having jurisdiction, often abbreviated as AHJ, believes the feeder is adequate despite its apparent undersizing is a point of contention. While the Army Corps of Engineers may have a role in a project, the ultimate authority having jurisdiction lies with the local electrical inspector. This inspector is responsible for ensuring that all electrical installations adhere to the National Electrical Code and local regulations. To address the situation, it is recommended to contact the local electrical inspector and request an inspection of the generator installation. The inspector will assess whether the feeder is adequate for the intended service and verify compliance with the applicable electrical codes. If the installation meets code requirements, the inspector will issue a certificate of compliance. However, if the inspector determines that the feeder is indeed undersized, they will require corrective action to bring the installation into compliance. This may involve replacing the existing feeder with a larger conductor, installing additional parallel feeders, or implementing other engineering solutions to ensure the system's ampacity matches the generator's output. The following is an explanation of ampacity and its importance. Ampacity is the current in amps that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. The National Electrical Code, or NEC, provides tables that list the ampacities of various conductors based on their size, material, insulation type, and installation environment. These tables are essential for selecting the appropriate conductors for any electrical circuit or feeder. Several factors influence a conductor's ampacity. Firstly, conductor size. Larger conductors have a greater cross-sectional area, allowing them to carry more current without overheating. The National Electrical Code specifies conductor sizes in terms of American wire gauge, or AUG, or circular mils, or KC mil. Secondly, conductor material. Copper and aluminum are the two most common conductor materials. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. Thirdly, insulation type. The insulation surrounding a conductor affects its ability to dissipate heat. Different insulation types have different temperature ratings which determine the maximum allowable conductor temperature. Common insulation types include THHN, THWN, THW, and XHHW. Fourthly, ambient temperature. The ambient temperature surrounding a conductor affects its ability to dissipate heat. Higher ambient temperatures reduce the conductor's ampacity. The National Electrical Code requires adjustments to conductor ampacity for ambient temperatures above 30 degrees Celsius, which is 86 degrees Fahrenheit. Fifthly, number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in the same raceway or cable, the heat generated by each conductor can raise the overall temperature, reducing the ampacity of each conductor. The National Electrical Code requires ampacity adjustments when more than 3 current-carrying conductors are installed in a raceway or cable. These adjustments are outlined in National Electrical Code Table 310.15. A3. The National Electrical Code provides tables that list the ampacities of conductors under various conditions. For example, National Electrical Code Table 310.16 lists the ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air and in raceways or cables. This table provides ampacity values for different conductor sizes, materials, and insulation types, taking into account the ambient temperature and the number of conductors in a raceway or cable. To determine the appropriate conductor size for a specific application, several factors must be considered. Firstly, the load current. The conductor must be able to carry the full load current of the circuit or feeder. Secondly, the voltage drop. The voltage drop in a conductor should not exceed 3% for feeders and 5% for branch circuits. Larger conductors have lower voltage drops. Thirdly, the ambient temperature. The conductor ampacity must be adjusted for ambient temperatures above 30 degrees Celsius. Fourthly, the number of conductors in a raceway or cable. The conductor ampacity must be adjusted when more than 3 current-carrying conductors are installed in a raceway or cable. The neutral conductor in a 3-phase system carries the unbalanced current between the phases. In a balanced system, where the loads on all 3 phases are equal, the neutral current is 0. However, in an unbalanced system, where the loads on the phases are unequal, the neutral current can be significant. The National Electrical Code requires that the neutral conductor be sized to carry the maximum unbalanced load. In most cases, the neutral conductor can be sized smaller than the phase conductors, but it must be large enough to carry the expected unbalanced current. For example, National Electrical Code Section 220.61 allows the neutral conductor in a service or feeder to be sized at 70% of the phase conductors if the neutral load consists primarily of nonlinear loads, such as electronic equipment. Nonlinear loads generate harmonic currents, which can significantly increase the neutral current. In these cases, the neutral conductor may need to be sized the same as the phase conductors or even larger. Now, let's discuss the authority having jurisdiction, abbreviated as AHJ. The authority having jurisdiction is the organization, office, or individual responsible for enforcing the requirements of a code or standard, or for approving equipment, materials, an installation, or a procedure. The authority having jurisdiction may be a federal, state, local, or other regional department or individual such as a fire marshal, building official, electrical inspector, or others having statutory authority. The authority having jurisdiction plays a critical role in ensuring the safety and compliance of electrical installations. They review plans, conduct inspections, and issue permits to ensure that installations meet the requirements of the National Electrical Code and local regulations. The authority having jurisdiction also has the authority to interpret the National Electrical Code and to make decisions on issues that are not specifically addressed in the code. The authority having jurisdiction is typically a local electrical inspector or building official. However, in some cases, it may be a state or federal agency. For example, the Occupational Safety and Health Administration, or OSHA, has authority over electrical safety in the workplace. The process of obtaining a certificate of compliance typically involves several steps. Firstly, submit plans and specifications. The electrical contractor submits detailed plans and specifications for the electrical installation to the authority having jurisdiction for review. Secondly, obtain a permit. Once the plans are approved, the electrical contractor obtains a permit to begin the installation. Thirdly, conduct the installation. The electrical contractor installs the electrical system according to the approved plans and specifications. Fourthly, request an inspection. After the installation is complete, the electrical contractor requests an inspection from the authority having jurisdiction. Fifthly, conduct the inspection. The authority having jurisdiction conducts an inspection to verify that the installation meets the requirements of the National Electrical Code and local regulations. Sixthly, address any deficiencies. If the inspection reveals any deficiencies, the electrical contractor must correct them and request a re-inspection. Seventhly, issue a certificate of compliance. Once the authority having jurisdiction is satisfied that the installation meets all requirements, they issue a certificate of compliance. The certificate of compliance is a document that certifies that the electrical installation meets the requirements of the National Electrical Code and local regulations. It is typically required before the electrical system can be energized and put into service. Here's a summary of the steps to take in this specific situation. Firstly, review the National Electrical Code requirements for feeder ampacity and neutral conductor sizing to ensure a thorough understanding of the applicable regulations. Secondly, document the discrepancy between the generator output breaker rating, which is 800 amps, and the feeder ampacity, which is 640 amps. Provide clear evidence that the feeder is undersized for the intended load. Thirdly, contact the local electrical inspector and request an inspection of the generator installation. Provide the inspector with all relevant documentation, including the generator specifications, feeder ampacity, and National Electrical Code references. Fourthly, cooperate fully with the electrical inspector during the inspection process. Address any questions or concerns they may have and provide access to the installation for thorough examination. Fifthly, if the electrical inspector determines that the feeder is undersized, obtain a written notice of violation. This notice should clearly state the specific code violations and the required corrective actions. Sixthly, develop a plan to correct the deficiencies identified by the electrical inspector. This may involve replacing the existing feeder with a larger conductor, installing additional parallel feeders, or implementing other engineering solutions. Seventhly, obtain approval from the electrical inspector for the proposed corrective action plan. Ensure that the plan meets all applicable code requirements and addresses the identified violations. Eighthly, implement the approved corrective action plan in a timely and professional manner. Ensure that all work is performed by qualified electricians and in accordance with the National Electrical Code and local regulations. Ninthly, request a re-inspection from the electrical inspector after the corrective actions have been completed. Provide documentation that demonstrates that the violations have been corrected. Tenthly, obtain a certificate of compliance from the electrical inspector once they are satisfied that the installation meets all requirements. This certificate will certify that the electrical system is safe and compliant with the National Electrical Code and local regulations. To further clarify the situation, let's consider some specific National Electrical Code sections related to feeder ampacity and neutral conductor sizing. National Electrical Code Section 215.2 Minimum Feeder Conductor Ampacity. This section requires that the feeder conductors have an ampacity not less than the sum of the non-continuous load plus 125% of the continuous load. National Electrical Code Section 220.61 Permissible Reduction of Neutral Conductor. This section allows the neutral conductor in a service or feeder to be sized at 70% of the phase conductors if the neutral load consists primarily of nonlinear loads. National Electrical Code Section 310.15 Ampacity of Conductors. This section provides tables and guidelines for determining the ampacity of conductors based on their size, material, insulation type, and installation environment. National Electrical Code Table 310.16 Ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius. This table provides ampacity values for different conductor sizes, materials, and insulation types, taking into account the ambient temperature and the number of conductors in a raceway or cable. It is also important to understand the concept of continuous load. A continuous load is a load where the maximum current is expected to continue for 3 hours or more. National Electrical Code Section 215.2 requires that the feeder conductors be sized to carry 125% of the continuous load. This is to account for the additional heat generated by the continuous load and to prevent the conductors from overheating. The National Electrical Code defines several types of overcurrent protection devices, including circuit breakers and fuses. Circuit breakers are devices that automatically interrupt the flow of current when an overload or short circuit occurs. Fuses are devices that contain a fusible link that melts and interrupts the flow of current when an overload or short circuit occurs. The National Electrical Code requires that overcurrent protection devices be sized to protect the conductors they supply. The overcurrent protection device should not be larger than the ampacity of the conductor. National Electrical Code Section 240.4 provides specific requirements for overcurrent protection of conductors. In the case of the 250 kW generator installation, the 800 amps breaker on the output should not exceed the ampacity of the feeder conductors. Since the feeder is only rated for 640 amps, the 800 amps breaker is too large and could allow the conductors to be overloaded. To correct this situation, the feeder conductors should be replaced with larger conductors that have an ampacity of at least 800 amps, or the 800 amps breaker should be replaced with a smaller breaker that is sized to protect the existing 640 amps feeder conductors. It is also important to consider the voltage drop in the feeder conductors. Voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends that the voltage drop in a feeder should not exceed 3%. To minimize voltage drop, larger conductors should be used. The National Electrical Code provides formulas and tables for calculating voltage drop. These calculations should be performed to ensure that the voltage drop in the feeder is within acceptable limits. In summary, the 250 kilowatts generator installation with an 800 amps breaker and a 640 amps feeder is a clear violation of the National Electrical Code. The feeder is undersized and could overheat if the generator is operating at full load. The Army Corps of Engineers is incorrect in stating that they are the authority having jurisdiction and that the feeder is adequate for the service. The local electrical inspector is the authority having jurisdiction and has the final say on whether or not the installation is compliant with the National Electrical Code. It is recommended to contact the local electrical inspector and have them inspect the installation. They will be able to determine if the feeder is adequate for the service and issue a certificate of compliance if it is. If the inspector determines that the feeder is undersized, corrective action will be required to bring the installation into compliance. This may involve replacing the existing feeder with a larger conductor, installing additional parallel feeders, or implementing other engineering solutions to ensure the system's ampacity matches the generator's output.